Okay, so let's unpack this. We rely on artificial intelligence for some of the most critical decisions in our lives. From a self-driving car navigating a tricky intersection to an algorithm performing, say, near-sensor medical diagnostics. Now imagine that AI tells you, I am 99% sure I know what this is.
But how do you actually verify that certainty? That's the problem, right? The core weakness of, well, almost all traditional AI systems today is that they're fundamentally deterministic. They're designed to spit out a single fixed answer.
And when they see something new.
Exactly. When they encounter data they weren't trained on, a truly novel situation, they often just, guess wildly. They can generate catastrophic errors or even fabricated information, but still report that same false, confident 99%. They might know the answer, but they have no concept of their own ignorance.
We need systems that can basically raise a hand and say, hold on, I am highly uncertain about this input. Maybe a human should take a look. That ability to quantify and communicate genuine confidence, that's the absolute frontier for trustworthy AI.
It really is.
So our deep dive today is into a pretty radical solution called Bayesian electronics.
And this is more than just a software fix. It's a fundamental shift in the AI hardware itself. The approach promises to create AI systems that are inherently robust, adaptive, and I think most surprisingly, highly energy efficient, especially for what we call edge AI.
Right. The small, constrained, low-power devices in everything from our wearables to, say, industrial sensors. And we're getting the blueprint for this transformation from the researchers who, well, literally wrote the book on it. We're looking at a perspective piece by Damien Querlios of University of Paris-Saclay and Elisa Vianello of University of Grenoble-Alpes. It was published in Nature Review's Electrical Engineering, and it really maps out how the physics of these tiny nanodevices can solve the big, abstract problem of AI uncertainty.
And to really understand the solution, I think we have to start with the problem itself. What makes this whole Bayesian idea so difficult to implement with our conventional digital chips?
Okay, let's start with that core difference. Traditional AI gives a single fixed answer. It says, the temperature is 25 degrees. What does a Bayesian model do instead?
A Bayesian model, well, it completely embraces uncertainty. Instead of calculating that one deterministic value, it assigns probability distributions to every single unknown parameter in the model. So it's the difference between saying the temperature is 25 degrees and saying the temperature is most likely 25 degrees, but I'm, say, 90% sure it's between 24.5 and 25.5.
That is so powerful. So if the model has high confidence, that distribution is really tight and narrow. But if it's seeing something ambiguous or totally unfamiliar, that distribution just broadens right out, and it automatically gives you an explicit uncertainty number.
Exactly. But there's a catch. Manipulating these high-dimensional distributions is computationally intense. To accurately approximate them, Bayesian algorithms often rely on a process called sampling, which basically means generating and evaluating millions of random values to get a sense of the full distribution.
And on a traditional computer, that process is just a huge drain on memory and energy.
A massive drain, which is why, Bayesian methods have mostly been confined to these huge, powerful data centers.
Okay, so this is where the physics of the nanodevice world comes in and just flips the whole script. We're talking about emerging memory devices, things like Memristors or phase change memory. For years, engineers have fought tooth and nail to make these things perfectly predictable, but the source points out they have this intrinsic randomness.
And this is the huge philosophical shift. I mean, for decades, the goal of microelectronics was absolute deterministic perfection. You suppress all noise, eliminate all variability. But now, with Bayesian electronics, that physical noise and variability, it's being embraced as a revolutionary asset.
Wait, hold on. So instead of spending energy to computationally generate randomness, we're just harvesting the natural, unavoidable chaos of the material itself. That feels deeply counterintuitive. If we're relying on device noise, how do we stop the system from becoming, too chaotic? Does the source talk about how they tune that chaos?
That's the core engineering challenge here. They aren't relying on total chaos. They're leveraging consistent, predictable sources of randomness. Things like the inherent device-to-device variability you see when you manufacture thousands of identical units. This physical noise, it acts as a built-in random number generator, enabling that probabilistic sampling automatically, and that drastically reduces the complexity and, critically, the energy costs.
So instead of computation being about fixes zeros and ones, it's about the statistics of physical events. Bayesian electronics recognizes that these nanodevices can store and manipulate probabilities directly within their physical structure.
And that changes the entire paradigm for hardware design.
So let's get into how this all gets structured. The source outlines two main Bayesian concepts that need dedicated hardware. First up, they detail something called Bayesian networks, or BNs.
BNs are, they're like a high-tech detective agency for sensors. They're these directed acyclic graphs used for symbolic reasoning and integrating prior knowledge. They're fantastic for what's called sensor fusion.
Sensor fusion.
Yeah, so if you have two or three noisy, maybe conflicting sensors reporting on an event, BNs use Bayes' law to efficiently figure out the most probable truth. They use those contextual priors to reconcile all that uncertainty.
Okay, so BNs are about making logical inferences from a bunch of uncertain inputs. But what about the AI that learns patterns, like an image classifier? That's where Bayesian neural networks, BNNs, come in, I assume.
That's it. BNNs replicate the layered structure of deep learning. But here's the crucial difference. Every single weight in the network isn't a fixed number. Every weight is modeled as a random variable with its own probability distribution.
And that right there, that distribution, it immediately gives us the safety mechanism we need, out-of-distribution detection. If the network sees an unfamiliar input, an image it's never seen before, the output distribution just widens dramatically, right? Signaling that it's not confident.
Precisely. It allows the AI to say, I see what you showed me, but I have no idea what it is, instead of just forcing a bad guess. And that's absolutely essential for safety-critical systems.
Okay.
So now we have to ask the hardware question. How do these nanodevices actually store and manipulate those probability distributions physically? The researchers detail three main strategies for this.
Okay, the first seems pretty straightforward: explicit storage.
Yeah, this is where you just store the parameters of the distribution, like the average, the mean, or the certainty spread, the standard deviation, or sigma. You store them in memory arrays, and then you use dedicated logic to generate the samples. It's simple conceptually, but it needs a lot of extra hardware.
The second strategy feels a bit more elegant. It's called population-based representation.
I agree, it is elegant. This is where you harness the collective power of a large group, an ensemble, of devices like filamentary memristors. The natural device-to-device variability across that whole population is used to statistically encode the distribution. So if you read, say, 10,000 of these devices, their slight differences become an asset, giving you statistical sampling at scale instantly.
Low latency, low overhead. And the third approach, device-intrinsic random variables.
With this one, instead of a whole population, you focus on the consistent high read noise of a single cell, like in what are called stochastic magnetic tunnel junctions, or MTJs. You just read that single cell over and over, and its predictable physical fluctuations become the source of randomness for your sampling.
But no matter which strategy they use, the research points to this one critical hardware hurdle: achieving independent control of the mean, the more, and the standard deviation, the sigma. Apparently, these two parameters are often correlated in physical processes.
It's like trying to independently control both the target, the mean answer, and the size of that target, the confidence spread, using the exact same physical knob. Because the underlying physics couples them, most current designs have to use, multi-device approaches, maybe 2 or 4 memristor cells per parameter, just to decouple those variables. That adds complexity, and achieving that control in a single device is a key open research question.
Let's pivot to the application side, which is, maybe the most impressive part of this whole thing. Edge AI desperately needs on-chip learning, the ability to adapt in real time without phoning home to the cloud. But it's so energy intensive. How does Bayesian electronics solve that?
Well, since Bayesian electronics is naturally good at inference, at figuring out probability distributions, it basically turns the whole learning process into an inference problem. You're just seeking the full distribution of parameters given the data, which allows for these incredibly energy-frugal updates.
And one method for that is Markov chain Monte Carlo, MCMC sampling. It's sort of a sophisticated way of wandering around a probability landscape to find the most likely answer. They ran a pretty powerful proof of concept with this, right?
They did. They used an array of over 16,000 memristors to train a system to detect cancer in mammography images. It matched the software accuracy 97%. But the kicker is the energy estimate. The researchers calculate that a final fully integrated system would only need microjoules of energy for the entire learning process.
Microjoules. Just to put that in perspective for you, that is orders and orders of magnitude less energy than a conventional computer uses. You could probably power that whole learning process with less energy than it takes to register a single click of your computer mouse. That's just transformative for a battery-powered medical device.
And it's not just MCMC. There's another method called stochastic gradient Langevin dynamics, or SGLD. This is incredibly clever. It takes the device's physical fluctuations, that noise we were talking about, and injects it directly into the standard learning process, gradient descent. That noise provides the random kick needed to escape local minima and explore the parameter space more efficiently.
And SGLD directly enables the killer app for industry, active learning. With active learning, you only ask for human labels on the data points that are most useful. And since the Bayesian model tracks its own uncertainty, it can just flag the data points it's most confused about and ask for a human label for only those points.
This efficiency is just a game changer. It dramatically reduces the need for these massive, expensive, pre-labeled datasets. The source highlights a milestone work. A Memristor BNN system trained for a robotic pouring task using this read noise-based SGLD. And the active learning meant that out of 10,000 examples, they only needed 128 human labels.
Wow. That's less than 2% of the data needing a human to look at it, and the energy savings were staggering. That system got over 90% success while using 153 times less energy than a conventional GPU implementation doing the same thing. That ability to adapt efficiently and minimize data reliance, that's the next generation of autonomy.
And there's one final key problem this whole framework solves. The infamous AI roadblock known as catastrophic forgetting.
Ah, yes, this is a huge issue. In standard deep learning, if you teach an AI a new skill, it just immediately forgets the old one. It's like you train a self-driving car on snow, then retrain it on desert driving, and it might suddenly forget how to handle ice.
Exactly right. Classical methods just overwrite the old parameters with the new data. But Bayes' law naturally mitigates this. It uses the old posterior distribution, the system's previous knowledge, as the new prior, so it effectively integrates new information seamlessly without corrupting what it already learned. This capacity for continual learning is crucial for any long-lived device, like an industrial sensor that has to cope with years of changing conditions.
It's just genuinely fascinating how we're finding answers to these high-level computational problems by looking at the lowest levels of physics. And it feels so, I don't know, organic. The research even draws these great parallels between Bayesian electronics and biology.
Absolutely. The leading hypotheses suggest the brain itself is fundamentally a Bayesian machine.
Yeah.
It's constantly integrating noisy sensory data with our prior knowledge and expectations, all in real time.
The free energy principle kind of formalizes this, right? It suggests that the brain's main goal is to minimize surprise, the mismatch between what it predicts and what it actually senses. And the math here is just so neat. Minimizing that surprise is mathematically the same as performing approximate Bayesian inference.
It is. And furthermore, even the irregular probabilistic spikes that neurons use to communicate, they might act as samples drawn from an underlying probability distribution, which mirrors exactly how Bayesian electronics uses nanodevice noise for sampling. It really seems like nature cracked this code first by embracing variability, not fighting it.
So looking ahead, how do we get from these incredible lab proofs of concept to real-world mass deployment?
The researchers really emphasize that the next phase requires a holistic design strategy. You can't just glue a Bayesian algorithm onto old hardware. It demands integrating the devices, the circuits, and the algorithms all together right from the ground up.
And to get the massive parallelism and memory density this needs, we have to move beyond 2D chips. So that means embracing 3D integration technologies.
Yes, exactly. Think about stacking memory and logic layers vertically, like building a skyscraper of computing components. That kind of architecture supports the massive parallel Bayesian operations needed, and it would significantly accelerate commercial deployment.
Ultimately, the real value proposition here is enabling truly trustworthy AI at the edge. When a low-power medical implant or an autonomous factory robot has high uncertainty, it can trigger a deferral or request for human input. It doesn't have to just take a risky, potentially destructive action. Trustworthiness comes from knowing the limits of your own knowledge.
It's about building safety into the fundamental physics of the chip, not just writing it into the code.
So to sum up this entire deep dive, I think we've learned 3 crucial takeaways about the future of AI hardware. First, trustworthy AI requires quantifying uncertainty. Bayesian methods do that by using probability distributions, not just simple fixed values.
2, Bayesian electronics harnesses the intrinsic noise and randomness of nanodevices like Memristors to perform highly energy-efficient sampling. And that leads to massive energy savings, like being 153 times more efficient than a GPU in one of those complex learning tasks.
And 3, This hardware shift enables on-chip Bayesian learning. It creates systems that are highly adaptive, require dramatically fewer expensive human-labeled data points, and can learn continually without that catastrophic forgetting.
And this isn't just about making AI faster or smaller. It's really a fundamental shift in our philosophical approach to computation. We're moving away from deterministic calculation and toward probabilistic inference, creating a system that inherently understands its own limitations. Just like the ultimate adaptive system, the human brain.
So here's a final thought. If our future AI knows exactly how certain it is about every single decision it makes, what fundamental human problems might we finally trust machines to solve autonomously? Think about that for a second. That's all the time we have for this deep dive. If you enjoyed getting to the bottom of Bayesian electronics, make sure you hit that subscribe button to keep receiving our insights into the cutting edge of science and technology.